generate our own regression line, like by hand, for our IAs. And these are the last set of statistics we need. So after this point, ideally, we'd be ready to, get our Excel sheets going and start getting our, our papers going, presuming we had the data, right? So please, over the rest of this week, try to work real hard on that, and we'll to get that data together so we can do that next week. Okay? All right. Let's begin here. So chapter 14 was all about bivariate analysis. That just means we're analyzing data that has two variables to it. So we've talked about like building a scatter plot, describing that using direction and shape and all that jazz. We talked about correlation last section, where we actually calculate that correlation coefficient, that value R, both using the Pearson method and the Spearman method. So there are two different R values that we calculated. Today we're going to talk about building our own regression line. Now, we've done this with the calculator already, right? We've used the calculator to do linear regression to get our R value. Today we're going to show you how this is done by hand. So a linear relationship between two quantitative variables, it's common, it's fairly easy to understand, it's usually pretty obvious. A regression line kind of summarizes that linear relationship. And we can use that then regression line to make predictions about if our independent variable is amount of sleep and our dependent variable is your ACT score, if you slept 16 hours a day, maybe we can make a prediction about what your ACT score would be, kind of thing, right? So again, this regression line describes how the dependent variable, the y, changes as the independent variable changes. So again, we often use that regression line to predict a value for y given a value of x. The type of regression line we're going to be talking about here is often called a best fit line, or more specifically, a least squares regression line. And we'll talk about why it's called a least squares regression line in a moment. But an example here, we have a scatter plot, and here's an example of a regression line drawn in. So our regression line equation is y hat. So that's a little symbol there. You read it as y hat equals mx plus b, where y hat is going to be our predicted y value. M is our slope, and b is the y-intercept, just like Algebra 1 pre-algebra from like a million years ago, except there's a hat on our y now. Oh dear! I think it'll be okay. Now, one thing we have to remember when we drew our regression line is that it had to go through the mean point. Remember that from last time? So keep that in mind. So in most cases, when we draw a regression line, we don't pass through any of the actual data points in our set, right? So what we're going to be interested in when we construct like how to do this regression equation by hand is something called a residual. So the residual is just the distance between our observed y-coordinate, so the coordinate from our data point, and our predicted y-coordinate the y value from the regression line at the same x. So like, here's that data set before. So each of these vertical bars is the residual for each of the data points. Everybody okay with that? Notice the equation is observed minus predicted. So what will that allow to have happen? It's going to allow negative values, right? So for example, if your observed point is below your regression line, you're going to have a negative residual for that data point or for that x value. Is everybody okay with that? So some residuals can be positive, some can be negative, depending on whether you're above or below your line of best fit. So far, so good? Okay. So let's say that we have the scatter plot shown below, which represents the relationship between the average number of points scored per game, that's our x value, and the number of wins, that's our y value, for 12 college football teams in the SEC. So if we plotted the data, we might notice, hey, that's like a pretty nice looking linear relationship there. So we went and calculated a line of best fit, which we found to be this. Y hat equals 4.37x minus 3.75. And we're asked to interpret the slope and the y-intercept of this regression in context. So if the slope is 0.437, slopes are rate, right? What would the rate on that be if the y is wins and the x is the number of points? What would the unit for 4.37 have to be if y is number of wins and x is the points scored? So if I multiply 4.37 by points, the unit on 4.37, the denominator must be points, right? Everybody agree with that? And if it's equaling wins, the numerator for 4.37 has to be wins, because if I wins per points, I multiply it by points, the point unit cancels and I'm left with just wins, right? So what this would be saying is that you get 4.37 more wins for each point scored. Does everybody feel okay with that? And then what would the y-intercept mean?
Minus 3.75 wins for 0 points.
Great. If you score 0 points, we'd expect you to win negative 3.75 games. Does that make sense in the context of the problem? Not really, but let's just roll with it, okay? All right. So calculate and interpret the residual for South Carolina, which scored 30.1 points per game and had 11 wins. And we're going to be using this regression equation. So the residual is y actual minus y predicted, right? Everybody's okay with that? Okay. So what is the y actual in this case?
11 wins.
11 wins, right? That's how many games they actually won. What will be the y predicted?
30.1 points times the
Great. The answer we get when we plug 30.1 into the equation. Let's see what we get when we do that. So when we plug 30.1 in, we get 9.4. So our residual would be 11 minus 9.4, so 1.6 wins. Is everybody happy with how we did that? Pretty easy, but you need to understand the vocab, right? Because these are terms that you probably haven't heard before. So what is this basically saying is that South Carolina won 1.6 more games than expected based on the number of points scored per game. Football players, what could that possibly imply? South Carolina ended up winning 1.6 more games than the number of points they scored per game implied. What might we be able to say about South Carolina's football team? Good at what? Well, they're winning more than their scoring should predict. How would you win games if you're not scoring as much as you'd predict? Defense, right? I would suspect that they have quite a good defense or special teams, or their kicking game is very good. There's some other piece to this, or you got lucky and won a couple of very close games, right? That could be the other thing. You just, you did well in the turnovers and you won a couple games that maybe you shouldn't have, or that were like one score kind of 50-50 coin flippy games anyways. But defense would be my first suspicion, right? If you're winning more games than your offense would predict, you must be winning some other way. Defense and special teams would be the obvious first thing I would look at. So if you have a different regression line, you potentially get different residuals, right? We've yet to talk about how we actually construct one of these things. The one that we want is the one that minimizes the sum of the squared residuals. So this is what we call the least squares regression line that we mentioned earlier. So here's the same data set we've been looking at, right? So this is our best fit line. If I draw one of the residuals and I square that value and I make a square out of it, and I do that for every point, everybody's okay with what you're looking at? So this is just a square based on the size of the residual. What we want to do then is we want to take that best fit line and move it so that the sum of all those areas is as small as possible. We want to minimize the area of those squares. Everybody's okay with that? That's what we mean by least squares regression line. Now, are we going to do this in practice? No. We've done this electronically with the calculator, right? But what the calculator's doing to do this is it's just employing a formula. So for our regression line, y hat equals ax plus b. I don't know why we've changed from m to a all of a sudden. Probably because that matches what the calculator says. The way we can calculate our slope is the r value times the standard deviation of the y's divided by the standard deviation of the x's. And the b value would be the y mean minus the slope times the x mean. So in your homework, when they ask you to calculate these values, this is how they're expecting you to do that. They're just using these two formulas. Everybody's okay with that? In your IA, when we construct our best fit line, when we show our work, what are we going to use? These two formulas. Okay? Now, in practice, how are we going to actually get the number? just going to do linreg on the calculator, right? The values for A and B should never be wrong unless you fat fingered a data point or something. But to show your work, this is how we show our work, is with these formulas. Is everybody okay with that? All right. So let's take a example here. So I think that this was, what was this data set? This was the value of an F-150 pickup truck dependent on the total miles driven or something. So the problem says identify the slope and y-intercept of the regression line. Well, right? Slope, y-intercept. Interpret the value in context. What would the slope be telling us?
Price goes down.
Yeah, can we be a little bit more specific than that? How much does the price go down per mile? So it would go down like 16.29 cents, right? Or $0.1629 for each mile you drive. So basically you're losing 17 cents a mile or something. Everybody okay with that idea? What does the y-intercept say?
The truck was worth $38,257.
Great. Brand new with no miles on it. The truck was worth $38,257. Yeah, perfect. So again, we said that the slope tells us that we're losing, 16.3 cents per mile, and that the 38,257 is the price of the value of the truck with 0 miles on it. What do you guys think? So far, so good. The other thing that we might be asked to do is to predict the price for a Ford F-150 with 100,000 miles on it. So to do that, we find 100,000 miles. We trace up and we trace over. Or you could plug 100,000 miles into our equation. You're both doing the same thing. Depending if you have just the graph, you'd have to do something like this. If you had just the equation, you'd have to plug it into the equation. If you had both of them, you could take your pick, right? So what does it appear that value is, or that price should be? 22,000 or so? You buy that? So we plugged it in and we get just about 22,000. So when we make a prediction using our best fit line, there's two types of predictions that we make. This is one example. Does anybody remember what this type of prediction is called? Well, let me give you a hint. The other type of prediction might be if we tried to predict something, when the truck has 200,000 miles driven. That's another type of prediction. So this type where the x value that you're plugging in lies in between the smallest x value and the biggest x value in your data set, this is called interpolation. Interpolation, typically these predictions are reliable. The other type of prediction, when you ask for like a 200,000 mile truck where the data or your x value is either much bigger or much smaller than the biggest or smallest x values in your data set, is called extrapolation. Those tend to be much less reliable because, well, you're not sure this linear relationship is going to continue forever. And in fact, we know, for an example, an automobile, that that's not going to continue forever because you're never going to get a negative value on a vehicle, right? What's the lowest the price could ever get to? Zero. And I would say even if you have like 350,000 miles, if the vehicle is still running and operable, it still is going to retain some value. It's never going to go to zero. But if it was inoperable and you had 15,000 miles on it, still price goes to zero, right? Or near zero. You guys feel okay? So that's the last piece of vocab. So again, extrapolation, we just talked about, and why they're not accurate. Interpolation is very good. So let's say we're using a regression line to make a prediction. We need two things for that prediction to be reliable. First thing is the regression equation that we're using has to be a good fit to the data. So you need an R value that's close to 1 or -1. If you have a lousy R value, doesn't matter if you do interpolation or not, it's not going to be reliable. Everybody agree with that? If you're using a bad model to describe what's going on, you're going to get all kinds of kooky results. Second thing we need to check is that we're doing interpolation as opposed to extrapolation. Even if you have a good R value, if you're predicting something way outside of your data set, not going to be reliable. So those are the two things that you have to have for reliable prediction. You have to have a good fit to your data. Your model has to be a good fit to your data. The R value has to be close to 1 or -1. And that you're doing interpolation. If you miss either one of those or both, unreliable. That's the problem with like climate change models, right? Because you don't have any data in the future. So you're always doing extrapolation. So the further you get away from the end of your data set that you use to construct your model, the less reliable those predictions get. That's why when people are talking about, oh, in the year 2300, you know, the temperature is going to be, it's like, that's hugely unreliable. You're so far away from what your data set has. Because really you only have reliable temperature data for like the past 100 years, right? Like, it's a very small data set, geologically speaking, right? The Earth's been around having temperature for a long time. Okay. And that's that. Let's go and pull up some of these questions and run through some examples. You probably need your calculator, right? So if you're following along, pull out that graphing calculator. And just as a reminder, like almost everything we do or have done in first semester, the majority of this chapter is once again about calculator literacy, right? If you understand like what to do with your calculator, there's almost nothing we're doing by hand here, right? It's just about how to use your calculator. All right, so let's say Carrie and Danielle want to investigate if tapping on a can of soda would reduce the amount of soda expelled after the can has been shaken. For their experiment, they shook 40 cans of soda and randomly assigned, each to be tapped for 0 seconds, 4 seconds, 8 seconds, or 12 seconds. Then, after opening the can and cleaning up the mess, the students measured the amount of soda left in each can in milliliters. Below are the data and a scatter plot. Everybody's okay? Describe the direction, form, and strength of the scatter plot. Who wants to do this one? Don't make me get out the random name generator. Alexis. Great, that's the direction. Form is linear, I'd agree. I'd say that's fair. Moderately strong seems okay to me. Why did we say it was positive? Because it has like a positive slope. It's going up from left to right. Good. And why'd you say it was linear? Because it looks like a line would fit through it reasonably well. Sure. And why did you say moderately strong?
Because the dots are pretty close together, but there's still a couple out.
Yeah, I think that's all pretty fair. Example 2, it says the equation of the regression line in the previous example is given as blah, 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 below. Identify the slope and y-intercept of the regression equation and interpret each number in the context of the experiment. Who wants to do this one? Can tell us the slope and y-intercept and what they mean in the context of the experiment. Okay, Diego.
So the slope is 2.63 milliliters maybe of soda remaining over tapping time.
Okay.
And
So what would that mean?
that this
For each second tapping,
there's 2.63 more milliliters of soda
remaining.
remaining.
Excellent. So again, you're just looking at one of the independent variable results in slope of the dependent variable. That's like the fill in the blank version of that, right? Good, and go.
And when there's no tapping, there's 248.6 milliliters of soda. Yeah. So that's
Remaining.
Yeah.
Yep. So that's not a full can, right? That's if you didn't do any tapping at all, and you have a huge mess. Everybody cool? All right. Example 3 says, using the equation above, determine what the predicted amount of soda remaining would be for the indicated tapping times if applicable. Isaac, are you doing this right now? I see you grinding on that calc. I'm going to call on you then.
For 5 cents, it'd be 61.75.
Great.
For 10, 274.9.
Good.
And then 3.7.5 to 30.
Nope. You didn't make an error on your calculator, though. What's the key phrase in this question? If applicable. Why am I shaking my head at 30 seconds? Yeah, this is extrapolation at 30 seconds. Should be disregarded as inapplicable. right? We talked about that just a few seconds ago, and I tricked you. Ha ha! Will I try to do that again?
Yeah.
Absolutely. Absolutely.
You put a little star next to it, just
Then it's not tricking. This, I find it pretty nice that I'm at least telling you that I'm planning on doing it again and pointing out what the trick was so that it's much less tricky the second time around.
so. You just write next to 30 seconds.
Yeah. Yeah. You would just say, like, this is extrapolation and should not be done or something. That would be fine. And even if you wrote down what the number was and then said this value should be disregarded because it's extrapolation, that would be fine, right? If Isaac listed what he did and then said, but we should disregard this value because it's found using extrapolation, perfect. No problem there either. All right. From the experiment performed on tapping pop cans in 10.2, or 10.02. What is 10.02? I think that just must be this example one. I don't know. Find and interpret the residuals for the indicated cans. Remember the formula. The residual equals y minus y hat, and this was our regression equation. So what about the can where we tapped for 4 seconds and had 260 milliliters of soda remaining? Who can calculate the residual for this? It's literally just 260 minus 4 plugged into the equation. That's it. So 260 minus the result of when we plugged 4 in here.
So minus prediction.
Should it get positive 0.88? That's good. So the residual would be 0.88 milliliters more soda remaining. So our actual, or our prediction undershot the actual value, right? Everybody's okay with that? That's what that's saying, that the actual value is more than the predicted value. Try it for part B. Who's got the number? Megan. Great. So we have less soda than the predict. That's negative, or 14.64 less soda than predicted, right? So there the prediction overshot what actually happened. Which again, if we go back and we look at our regression line, should not be a surprise, right? Like some of the 4s were above and some of the 4s were below. Some of the 8s were, at every time there was some data that was above the prediction, below the prediction, right? Okay. Example 5, we designed a study to investigate the relationship between the row that a student is sitting in and their grade on a particular test. We make the row numbers our independent variable with a row value of 1 indicating the closest to the front of the classroom. Based on our data, we found the following statistics. Yada, yada, yada. Use the formula below to find the regression equation for the linear regression. Interpret the values for the slope and y-intercept in the context of the equation. So you're writing this equation, and it's telling you that to calculate the m, you need to do this, and the b, you need to do that. I think this is our last question. Oh, no, there's one more. What did we get here, homies? Somebody got a slope for us yet?
Y equals
Oh.
negative 1 point, y hat equals negative 1.1 2 x plus 85.7.
Great. That's what I got. What does that mean in the context of the question?
What was y again?
Test score.
It's negative. So
Mm-hmm.
test scores go down by negative 1.1.
You can just say 1.1 if you say go down, right?
Go
Because
down by 1.1 when they're further away.
for each row,
For each row,
you move further back. Yeah. Diego, read your equation again.
y hat equals negative 1.12 x plus 85.7.
Which is correct. And then what does the y-intercept mean?
The highest grade on the test was 85.
No. Means if you're sitting in row 0, I mean up here somewhere, we'd expect you to get an 85.7. So the highest grade could have been in row 4, because our R value, if you looked at this problem, was not very good. So I'm guessing this data was kind of all over the place. But that's what that would mean. Does that make sense? Again, remembering x's is rows. And in a situation like this, sometimes, I would say oftentimes, it's helpful to write our equation like we did up here, where I might call this test score equals m times row you're sitting in plus b, right? Like that helps just kind of like contextualize the problem with the numbers in there. I think that really helps me anyways remember, like, what am I talking about here? All right, let's Do it, big boy pants time. 10 students in a mathematics course measure their height in inches and weight in pounds to see if there's any correlation between the two measurements. They make the values of the height the independent variables. The table below gives the recorded values. Use the calculator to find a least square regression line for the data above. Yes, already have this in. Good. I think we've used this data set before. So when I do this, my linreg here, you see where it says store reg EQ? I'm going to take advantage of this, and I'm going to store my regression equation into Y1. So to find the Y1 in my calculator, I'm going to press vars, go over to yvars for the Y variables. Our calculator will always be in function mode for this class, and select Y1. Hit calculate. There's all my stuff. And now if I look at the Y1 spot, I notice that that equation's already been typed in there for me. So if I round that, how should I round that value? 3 sig figs, right? $7.51 and then minus 331. Unless it tells me otherwise, it didn't tell me what to do there. Check the equation for the regression using the following formulas. Okay, so here's what I would do. I would do stat, calc, 2 variable stats, L1 and L2. And now I'm going to do R, so I'll go vars, statistics, and I think, let's see, where is that at? Not in that one. There, that's it. R times, and let's do the fraction here. And I'm going to pull sigma y, so I'll go back vars, statistics, oh boy, statistics, sigma y, and then vars, statistics, sigma x. Uh-oh. Oh, I didn't like that, huh? Okay. Did yours work?
Yeah.
It did. Interesting.
I did parentheses.
You did parentheses around that?
Yeah.
Boy, that's strange. No? Okay. Well, let's try this one more time. There, it worked. Apparently it cleared the R value at one point for whatever reason, I don't know. And then if I do the other equation, oh, I lost my thing. pull that back up. So y bar minus m times x bar. So vars statistics y bar minus m, so vars statistics equation. Oh no. No, that's not going to be it. I doubt it. No. Points? No. Is it over here? Maybe I don't get it.
I guess we'll just do answer.
Yeah, that's true. We could just do answer. That is a good point. So second negative sign times x bar. So zoo var stat x bar. Feel okay? Calculatoring. And then use the scatter plot to graph the data as well as your linear regression. So I'm going to go stat plot, going to turn stat plot 1 on. Make sure the option, the type, first type is selected and we're using L1 and L2. And then I'm just going to do zoom statistic or zoom stat. There it is, number 9. And because I stored that reg EQ into Y1, I have that already for me. And I bet we could do this. Watch this, stat, edit. Let's say we wanted all the residuals. That should be L2 minus Y1 of L1, right? Should be the observed minus the predicted, and we're getting the predicted by plugging the X value into L1. Yeah, I thought that would work. Look at that, there's all the residuals if you need to do that. That's way easier than doing it by hand a bunch of times, right?
It's just a Y1.
Same way we did it before. We did vars, y vars. Yep. That's pretty slick, right? I suspect in the homework they're going to ask you for a bunch of residuals, and boy, that makes life pretty simple. So what I did up here, where it says L2 or L3, I did L2, which is the actual, minus, and I did vars, y vars function y1 of the x values from L1. And then just pressed enter and it populated the list with all the residuals. Which is pretty rad, right?
A bigger number means that it's further away from the regression line.
You can think about these as distances. So like that 26 means that the actual value is like 26 units above the regression line. But like a negative 17 would mean that it was like 17 units below the regression line. So they're both like very far away, but in opposite directions, right? What's up? Are you typing it into the title L1 or are you typing it into the yeah, so you have to make sure you're typing it into the list and not into an entry. You can't put a list into an entry. You can put a list into a list. It's like a data type thing. What do you guys think? That's it for this chapter. It's not so bad, right? I haven't graded your quizzes yet. I should have those for you next class. It's on my to-do list for today. But I haven't done it yet. You know what I'm saying? It happens, right? All right.